Hello students, myself Dr. Sanjay Kumar, and we will discuss our second paper, which is electricity, magnetism and electromagnetic theory. And in this paper our first unit belongs to electricity part, and to do this electricity part we should have some basic background about scalars and vector quantities, which I hope you all have. And I request you all, please go through that basic vector algebra from your plus 2, so that you will have better understanding of this unit. So till now, what we aware of scalar quantities and vector quantities. Scalar quantities we all know are the quantities having magnitudes only, and the vector quantities are those quantities which having magnitudes as well as directions, are known as vector quantities. Now we extend this concept to fields. So now we will define two more terms, which are scalar fields and vector fields. So first we will define scalar fields. So scalar field is nothing but the space or region of space in which we are considering something. Okay, in that space we have scalar quantities which are continuous within that given space. Means if we move from one point to another point in that prescribed region or prescribed space, then that scalar function is defined at all the points, and that space in which these scalar quantities are continuous are known as scalar fields. For example, suppose if we consider the temperature inside a room, then within that room, if we move from one point to other point, then the temperature might get changes from one point to another point, but we have at least some temperature at every point within that room. Okay, so that is an example of that scalar field. Means within that room temperature is a scalar field. Okay, another example, suppose we want to measure the gravity acting on a body that depends on height. Okay, the gravitational force, as you all know, it depends on the potential energy of any particle having some distance from the ground level is different. If you changes the height, then the gravitational force acting on that point will get changes. Okay, so that is another example of scalar fields. Okay, so now if we want to define a field, only field. So what is a field? Field is a region where a physical quantity possesses different values at different points. Thus the field may be defined as the region in which functions specify a physical quantity. Okay, and this field, depending on the quantity which we are defining, is it a scalar or a vector? So depending on that, the fields can be of two types, scalar field or a vector field. So scalar field, as we already discussed what it is, if in a given region of space we are defining a scalar quantity which is continuous within that given region of space, is known as scalar field. Examples of that, another example of scalar field is electric potential variation around a charged body. That is also an example of scalar field. Okay, and now suppose this can also be possible in a given field or a scalar field. There is quite a possibility that we have many points in that given field where the function, that scalar function or scalar quantity, has the same value. Okay, this can be possible. We can again we can discuss, suppose inside a room we can definitely maintain a constant room temperature. That means within that room at all the points within that space the temperature is same. Okay, so if we meet all those points within that space having same value of that scalar field, okay, then we will get a surface, and that surface over which the scalar field has same value is known as level surface. Okay, this you will understand. For example, In case of electric potential, such a surface is known as equipotential surface. This you already you might know in your plus 2. Or another example for the temperature case, suppose if we draw a line, a straight line over which temperature is same throughout that line, then that line is also known as isotherm. Similarly, we can discuss that isobars, okay, where the pressure along that line remains the same. Okay, so those lines, those surfaces over which a scalar quantity remains the same is known as level surface. In general, we call it as level surface, but for different scalar quantities like electric potential, we call it as equipotential surface. For temperature, we call it as isotherm. Okay, mathematically we can represent this scalar field like this. Suppose we have this function phi. Okay, we have this function phi, which is a function of a position vector r, and which itself is a function of r is a position vector in space, so it has coordinate x, y, z. So phi is a scalar field which can be defined as phi is a function of r vector. That means phi is a function of x, y, and z. Okay, so this is how we define scalar field. Okay, and now we come to the vector field. Similarly, we can define the vector field like we defined scalar field. The only difference is that in a scalar field we have a scalar quantity which is defined within that region of space. In vector field we have that vector quantity, okay, which is continuous at each point in that field. Okay, and as we know, a vector quantity has its magnitude and direction. Okay, so each point in such a field is characterized by a vector quantity having definite magnitude and direction at that point. Okay, the example of vector fields are electric field, magnetic field, gravitational fields. These are the example of vector field. And as we know, the vector fields are represented by the lines or the flux lines. Okay, and the tangent at any point on the given lines gives the direction of vector field at that point. Okay, and the magnitude of that vector field is given by the number of field lines passing through an infinitely small area perpendicular to the field lines. That quantity is known as flux density at that point. Okay, again what we are discussing here, we are discussing a vector field. So in that vector field, the quantity, physical quantity, has to be a vector, and if it is a vector, then it has magnitude and direction. So what we are discussing, how we define the magnitude or the direction of that vector field. Okay, so the direction of any vector is defined as tangent at any point on the line. Okay, because vector fields are defined by the lines, field lines. Okay, we can draw some field lines like this, say these are the field lines. So at these field lines, if we want to know the direction at any particular point, so this particular point we want to know the direction, so this will be the direction. Okay, that will be the tangent on that curve, will give the direction of that vector. Okay, and the number of field lines crossing at this particular point will give us the magnitude of that vector. Okay, which is known as the flux density at that point. Okay, mathematically a vector field is represented by a vector quantity. Say E is a vector which is a function of, again is a function of position vector r, which is which depends on space coordinate x, y, and z. So that is how we define the vector field. Okay, I hope you understand the difference between scalar field and vector field, which is nothing but the So I hope now you have understand the difference between scalar field and vector field. I again want to summarize this. Means first we have defined a field. Field is what? We have a region of space in which we define any physical quantity. Okay, and that physical quantity in that region of space has to be continuous at all the points. If that field is there, that region of space is there, is known as field. If that physical quantity is a scalar quantity, then it will become scalar field, and if that physical quantity is a vector quantity, then it will become vector field. Okay, so I hope now you have understand the difference between scalar field and vector field. Now we move to another topic, which is line, surface and volume integrals of a vector and their physical significance. This topic is again is your basic related with this chapter, which we need to understand. So first we will define line integral of a vector field. So suppose we have this x, y and z coordinate system in which we have 2 points A and B which are in a given vector field. Okay, because what we are calculating the line integral of a vector field. So we have considered a region of space in which we have this space coordinate x, y and z, and in that region of space our vector field is, say, it is represented by A. Okay, and now in this region of space we want to calculate the line integral of that vector field A over any given path, say from point A to B, which you are seeing in this figure, from this A to B. Okay, the line integral is taken along that given path that runs from A to B, and along that path, suppose the displacement dr is a very small segment which we have considered. Okay, so what will be its line integral? If we calculate the scalar product of A and dr is taken along the path for each small interval. Okay, if we divide this whole path A to B into small segments, okay, and one such small segment is, say, it is dr, and if we calculate the scalar product of A dot dr, okay, and we calculate this product for all the segments, okay, between A and B, and if we sum up all these segments, okay, then what we will get? If we reduces this small segment to an infinitely small value, suppose dr approaches to 0, okay, so in that case this sum approaches to a line integral. This summation, this scalar product of A dot dr will become integral of A to B A dot dr. Okay, so that means what? The line integral of A to B A dot dr, what it represents? It represents the sum of scalar product of A and dr taken along all over the length of the path A to B. Okay, it is nothing, the line integral is nothing but this sum of scalar product of A dot dr taken over that given path. Okay, so that is known as line integral of the vector field. So now we will discuss its physical significance. The examples of line integral are, one of the example is we generally take line integral of electric field taken over the path AB is equal to the potential difference between A and B. Okay, you must have aware of this example. E is equal to minus dV over dx. Okay, E is electric field and V is the electric potential. So this expression you all know in your plus 2, you have done that. Okay, so that means if we want to calculate the potential V, it will become E dot dx. Okay, and if we integrate that, then it will be dV will become V. Okay, and E dot dx. So the line integral of electric field E taken over the path AB is equal to the potential difference between the points A and B. Okay. Another example, if we take the line integral of force taken over any path F dot dr. Okay. So what it will give us? It will give us the work done by the force in displacing a body from one point to another point. Okay. And suppose in a vector field, if the line integral over any closed path is 0, okay, this can happen if we move from A to B and then again from B to A. Okay, if we form an closed loop, and along that closed loop, if the line integral of any physical quantity is 0, okay, then that field in which the line integral around the closed path is 0 is also known as conservative field. This is very important result of this line integral of field, which we will use in future in this paper. Okay, so you need to remember line integral of any vector field over a closed path. If it is 0, then that field is known as conservative field. Okay, so now we move to second part of this, which is surface integral of a vector field. So to discuss this thing, first of all you need to understand a surface. A surface is also a vector quantity. Okay, a surface area is also a vector quantity. Okay, its magnitude is given by that surface area itself, and the direction of that surface is always along the direction perpendicular to the surface outward. Okay, so in this case what we have considered a surface S in a given vector field, okay, which is defined by A, and let us consider a small element of area ds on the surface S. Out of this surface S, we have considered a very small part ds. The area element ds is a vector quantity because the field itself is a vector field, so it is defined by vector quantity A. Okay, and its direction is given by a unit vector n cap. Okay, the area has a direction which is along n cap, which is normal to the surface directed outwards. If we have surface like this in this plane while we are watching our mobile, then the normal directed outwards will be from this surface of mobile to our face. That will be the direction of the normal. Okay, and let A be the vector acting in a direction making an angle theta. Okay, so in this surface, the vector field at that particular point, at that particular small segment, area segment, is directed along A. Okay, which makes an angle theta with the direction of that small segment. Okay, with the n cap. Okay, so that means the component of A along n cap will be A cos theta. This we all know. Okay, the component of A along n cap will become A cos theta. Okay, the number of the flux line crossing through the element area ds is given by this. Okay, if we take the dot product of A dot ds, okay, which is nothing but A ds cos theta, because theta is the angle between A and ds vector. Okay, this term we can also write as this. A dot ds will also written as this, A dot n cap. Okay, because the ds vector, this can be written as this A dot n cap ds, and we can remove the vector over this ds element. Okay, or we can write this term as A dot ds vector. Okay, so both terms have the same meaning. Okay, so what we have written here, A dot ds will be A ds cos theta. So this is the flux through this area element ds. If we want to calculate the total flux through the complete surface S, so what will be that? That will be the integral over this whole surface integral over this whole surface, which is this value, surface integral of A dot ds, okay, over the complete surface S. Okay, and as we already discussed, this element a dot ds, this term also we written as a dot n cap ds. Here we remove the vector over this ds and we have retained this n cap, which is the direction normal to the surface. Okay, so now we will discuss its physical significance. So if any surface area S is placed in an electric field S, then the surface integral of that electric field means this thing, integral of electric field over the surface, that will give us the total electric flux passing through the surface. Okay, this we will calculate in our coming chapters. The another example of the surface integral is, we will take surface integral of magnetic induction, that will give us the total magnetic flux through the surface S. Okay, so with the surface integral, what we can measure, we can calculate the total electric flux through a surface or total magnetic flux through a surface and many things. Okay, now we come to our third part, which is the volume integral of a vector field. How we will calculate this volume integral? So consider a closed surface enclosing the volume V in a vector field A. Okay, in the given field, which is our XYZ Cartesian coordinate system, in that given field we have considered a closed surface, okay, which encloses the volume V inside that vector field A. Okay, so the small volume element, if we take out of this complete volume, say dV will be dx, dy and dz. Okay, and if we take the volume integral of that a dV over the complete volume V, that will be this thing. Okay, in general, this volume integral we just write like this. Okay, but because in volume we know there are the three dimension x, y and z, so we represent, sometimes we represent this like three integrals over the volume. Okay, if it is surface, then there are two integrals, but in general we denote this terminology as simply by a single integration sign, and we just put this suffix there. If it is S, that means it's surface integral. If it is V, that means it is volume integral. Okay, so this volume integral will give us the space integral of that vector field A for the entire volume V. And the physical significance of this volume integral, we do calculate, we can calculate the charge density which represent the the physical significance of this volume integral is this: if we know in a given region of space, if we know the charge density, how that charge is distributed within that volume, if we know that, okay, then with the help of this volume integral, what we can calculate, we can calculate the total charge enclosed in that surface. Okay, this value we can calculate. This is actually total charge enclosed. This value we can calculate if we know the charge density rho. Okay, then we can calculate the total charge q within that volume. Okay, so this is the physical significance of this vector integral of volume integral of vector field. Okay, so I hope you have understand this, and this is our first lecture regarding the basic of vector algebra, which we are going to use in our coming classes. Thank you.